So students, good afternoon, and today I am going to tell you about Slater's rule and its application. And let me tell you what are the topics I will be covering here. So those will be Slater's rule, calculation of sigma, that is screening constants using Slater's rule, then applications of Slater's rule, and also some of the related questions. So before going to Slater's rule, let me tell you about a term which is called the effective nuclear charge, because we will be using this Slater's rule to calculate this effective nuclear charge. And what is the effective nuclear charge and why we need to know about that I am telling you now. You see this picture here, this is the nucleus and these are the electrons present in an atom. So there will be attractive force between this nucleus and the electrons present here. But other than this attractive force, there will be some repulsive force also, because here the electrons are present with like charges. So this repulsion and these electrons, as they shield this nucleus, you can see very well. So what will happen because of this? These outer electrons will fill the nuclear charge less effectively. That means these electrons are acting as a shield or screen, and they will make this nucleus actually shielded. So the result will be that these outermost electrons will be filling the nuclear charge less. So you see here, this is the equation to calculate the effective nuclear charge, which is called Z star. And we have to subtract this sigma value, which is called the screening constant value, to know about this Z star value. And this sigma we are going to calculate using the Slater's rule. So effective nuclear charge is the apparent nuclear charge felt by a valence shell electron and is calculated by subtracting the screening constant value from the actual nuclear charge. And this Z is the actual nuclear charge. Screening constant sigma takes into account of the effect of electrons closer to the nucleus. That you can understand very well. As the electrons will be close to the nucleus, that will be shield the nucleus more effectively than the outer electrons. So we will be calculating sigma, and for that we need this Slater's rule. So the Slater's rule, the first rule tells us that write the electronic configuration of the atom in the following order and groups. So what is that order and groups? You see here, the group electronic configuration is written like NS, NP are together and D and F are kept separately. So everywhere you can see with the same principal quantum number, S and P orbitals are kept in a group, and other D and F orbitals are kept separately even if they have the same principal quantum number. So let us take an example of fluorine. It has the atomic number 9 and the electronic configuration is 1s2, 2s2 and 2p5. So if we write the group electron configuration following this order, it will be like 1s2 and then 2s2p we will be writing together, and it will be 7. So where from this 7 has come? This 5 plus 2 is making it 7. Now we will go for another atom, zinc. So its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s2. So what will be the group electronic configuration? Following this rule, you see here I have written 1s2, then 2s2p will be writing together, and it will be, number of electrons will be 8. 6 plus 2, it will be 8. Then we will be writing 3s and 3p together, and it will be also 8. And then 3d we will be writing separately, and it will have number of electrons are 10 here, and we will be writing the 4s also separately. So coming to the second rule, what it tells us? It tells us that electrons in the right side of the electron of interest contribute nothing to the shielding. This is very simple. So electron of interest means the electron on which we are going to calculate the effective nuclear charge, that is the sigma value as well. So the outer electrons will not contribute to the shielding constant value. So that is very simple, because they are outside, and if your nucleus is here, this electron will take part in the calculation of sigma value, not the electrons which are outside of the electron of interest. Now coming to the third rule. What does it say? All other electrons in the same NS-NP group as that of the electron of interest contribute 0.35 nuclear charge units. I am going to tell you in detail about that, so you will understand that what is the meaning of this rule. And also you will learn that for 1s orbital a value of 0.30 works well. So let me explain you. Like again we are taking the example of fluorine. It is 1s2 2s2p whole 7. This is the group electronic configuration. So if we want to calculate the sigma value for 1 2p electron, what we will do? We will not take the number of electrons as 7, which will contribute in sigma. Instead we will take it as 6, because we are taking one electron on which we are calculating sigma, so that will not contribute in the calculation of sigma value. That's why we will be taking it as 6. And Slater rule tells us that this is the NS-NP group, so other electrons, that means the 6 electrons, will contribute 0.35 value. So it will be 0.35 into 6 from this NS-NP group, which will contribute for the sigma value. Now let us take example of lithium, whose group electronic configuration is 1s2 then 2s1. Now if we calculate the Z star on a 2s electron, on this 2s electron, so we are not going to consider this 2s electron, and this will not contribute in sigma. So what will contribute in sigma is this inner 1s2 electrons. That means 2 electrons in the 1s cell, and the value will be for 1s, it will be 0.30. So it is stated in the Slater rule. So we will do a multiplication of 0.30 into 2 for calculating sigma here. So this will not be 0.35. In case of 1s electrons, we are going to take this value as 0.30. Now coming to the fourth rule. It states that if the electron of interest is in NS or NP group, all electrons in the next inner group, that is N-1 shell, sealed to an extent of 0.85 each. So let me tell you. So this is fluorine again. So this group electronic configuration is known to you now. Now this 1s group this 1s group is actually called the N-1 group. So look at here. This is 2s2p, that means NS-NP group. This is having 7 electrons. So this is the nth group. And the inside there is a 1s group. 1s2 electrons are there. And the principal quantum number for this is 1. Here it was 2 and here it is 1. So this is called the N-1 cell. And for that the contribution will be 0.85. Here the contribution was 0.35, and now in the inner cell the contribution is more and it is 0.85. So this is obvious. You can understand that this will be more close to the nucleus, and as it will be close to the nucleus, it will shield the nuclear charge more effectively than these outer electrons. So the contribution is more, and it will be calculated as 0.85 into 2 for this part. The sigma contribution will be 0.85 into 2. So till now we have seen how to calculate the sigma value if we have electrons in the nth cell and N-1 cell. Now think if you have some more electrons as well. That means if you have electrons in the N-2 cell also. So what will be the contribution? The contribution here will be 1. That is, this is more than the contribution from the n-1 cell. This is also you can understand now, because these are close to the nucleus and this will contribute more. So that means this n-2 cell or less than n-2 cell all will contribute 1. So all electrons in the still lower groups, that is n-2 or lower, shield completely. As it is 1, so it is we are telling it that it will shield completely, and their contribution for this is unity. And now you see the calculation part. So here this is your nth electron. So n cell electron, and this will give rise to the value 0.35, and 0.35 we have multiplied by 1, as we are taking one electron on which we are doing the sigma value calculation. We are not taking into account about that, and then we will go for n-1 cell. What will happen here? Here you have 10 plus 8, that is 18 electrons. So as I have already told you, the contribution will be 0.85 for n-1 cell. So it will be 0.85 into 18, and these are the n-2 or less than n-2 cells. So what will happen for that? That will we have to multiply this value, the number of electrons value, with 1. So this is here, you see 8 plus 2, it is 10 number of electrons, and the value is 1 here for the screening constant, and this gives rise to the total value of sigma as 25.65. Now the another rule which tells us that if the electron of interest is in ND or NF cell, then all electrons to the left, that is all lower lying electrons, contribute 1 to the shielding constant value. So this is very important, and this is something different, so you have to remember this very carefully, and this is applicable only when you are going to calculate the sigma value for the ND or NF kind of electrons. So here is the group electronic configuration for zinc, and you see here you have 1s electron, 2s2p group is there, 3s3p group is there, and 3d10 is also there, and there were also 4s2 electrons. But here we are going to calculate the sigma value on one of these d electrons. So here we consider this as n cell, and the electrons other than the electron of interest, that will be 9 in number, will contribute 0.35. So we have multiplied here 0.35 into 9. We are not going to consider this 4s electrons, because we are going to calculate sigma on this 3d electron, one of this 3d electron. Now according to this rule, what happens? We have to take all these electrons together. That means 8 plus 8 plus 2, and this will give rise to 18 number of electrons. And this 18 number of electrons, we have to multiply it by 1 to get the sigma value. And you see here, I have done it like 0 into 2, because this has no contribution, then 0.35 into 9 plus 1 into 18, and this gives rise to a value of 21.15. This is the 7th rule about Slater's rule, and here what is said here, that shielding constant value is a summation of all the contribution from steps 2 to 5 and should be subtracted from nuclear charge to get the effective nuclear charge. That means Z star is equal to Z minus sigma. Now I have tabulated here the values, whatever I have told you earlier. You can check it. Like for electron groups, one is for the same group you have a contribution of 0.30. For the NSNP group, higher groups will be always, for everywhere it will be having a contribution of 0. Then for NS and P, same group will have a contribution of 0.35 and group N-1 will be 0.85. You can recheck them from the Slater's rule. And then groups less than equal to N-2 will contribute 1. And for ND and NF kind of electrons, you will have, for the same group you will have 0.35 and groups N-1 or N-2 all will contribute 1. So look at these pictures. I have done it for you so that you can remember it. You see, this is the nucleus, this is the NH cell, this is N-1, this is N-2. And for NS-NP kind of electrons, we will have, for N, the contribution will be 0.35. For N-1 cell electrons, the contribution will be 0.85. And for N-2, it will be 1. You can see as we are going inside, the contribution towards the sigma value is becoming more. And this is for the ND or NF kind of electrons, where you can see for this N group, you have the contribution 0.35. But for N-1, N-2, everywhere you have the contribution of 1. Here are actually two examples to calculate the sigma value. So which is, I have discussed these things earlier also. So just here is the summation. Like for fluorine, it is 1s2 group electronic configuration will be 1s2, then 2s2p together, and it will be 7. Now the contribution from this part will be 6 into 0.35 and contribution from this part will be 0.85 into 2. Why? Because this is the N-1 cell and this is the NH cell. And you see the sigma value for calculating for one of these 2p electron will be 3.80. So Z star will be on this 2p electron Z minus sigma, and it will be 9. It is the atomic number of fluorine, minus 3.80 is equal to 5.20. Now if we want to calculate the sigma value on one of these 2s electrons, so what we will do, we will not take in consideration these 2p5 electrons. So the contribution from these p electrons will be 0. Now what will happen here? So these 2s electrons are there and 1s electrons there. So from these 2s electrons, as we are going to calculate on one of these 2s electrons, so we will not take one electron, we will take only the remaining one electron which will contribute for sigma, and that will be 0.35 into 1. And then this inner electrons, that is 1s electron, here this is the N-1 cell and this will contribute 0.85. So it will be 2 into 0.85 and the value will be 2.05 after summation. So Z star felt by this 2s electron will be Z minus sigma is equal to 9 minus 2.05, and it will give rise to a value of 6.9095. So this is the problem 2. Find the shielding constant of 3d and 4s electrons in case of zinc atom, which has the Z is equal to 30. So the electronic configuration for zinc, as you know, that it will be 1s2 2s2 2p6 3s2 3p6 3d10 and 4s2. So for calculating sigma, first we have to write the group electronic configuration. So it will be, like you know, 1s will be separated, so 1s2, then 2s 2p will be together, 2s 2p will be whole 8, and 3s 3p will be also 8, and then 3d10 we have kept it separately, and 4s also we have kept it separately. Now first we are going to calculate the sigma value on one of these 3d electrons. So number of electron for 3d we are going to consider it as 9. And for here the contribution will be 0. So 0 into 2. Now 9 into 0.35, and as it is a d electron, so for all these inner electrons the contribution will be 1, and that will give rise to a value of 1 into 18. So the total value will be 21.15. And then the Z star, that is the effective nuclear charge felt by this 3d electron, will be Z minus sigma is equal to 30 minus 21.15 is equal to 8.85. Now we also want to know what will be the Z star on one of these 4s electrons. So for that, what will happen, we have to consider this 4s electron now. And now as this is a ns electron, so contribution for this one of the remaining electron will be 0.35. So we will write 0.35 into 1. Now for this n minus 1 part, we will be writing as this will be 10 plus 8, 18 into 0.85 into 0.85, and then we are going to the n minus 2 cell where it will be 8 plus 2, 10, and the contribution will be 1, so it will be 10 into 1, and the resultant value will be 25.65. So the Z star felt by one of these 4s electron will be Z star is equal to Z minus sigma is equal to 30 minus 25.65, and it will be 4.35. So now coming to the application of Slater's rule. First, you always you know that the cation is having the smaller size than the parent atom. This is obvious because as the when the cation is formed, the number of electrons become less in the outer cells, and this less number of electrons will be more closely attracted by the nucleus, and the size will obviously it will be less than the parent atom. But now we can tell this quantitatively using the Slater's rule. So let us consider beryllium and beryllium-2+. So for beryllium, the electronic configuration is actually 1s2, and the group electronic configuration will be 1s2 and 2s2. Now for calculating sigma, I have written here, you can see 0.35 into 1. That means contribution from this part will be 0.35 into 1. Then the inside we have two other electrons which are coming from 1s orbital, and as this is the n minus 1 cell, so contribution will be 0.85. So this addition will give us a value of 2.05, and then the Z star will be 4 minus 2.05, and it will give rise to the value of 1.95. Then look at here. So here you have the sigma value for the beryllium 2+, and you see here the value will be 0.30 into 1, as after the ionization the group electronic configuration will be only 1s2, and for the 1s electrons you know that we consider the value as 0.30. So you will get the Z star value as 4 minus 0.30, and it will be 3.70. So you can see clearly that the Z star for beryllium 2+ will be much greater than the Z star for beryllium. What does this indicate? This indicates that the electrons will be pulled towards the nucleus more if the Z star is more, and that will result in the size of the ion will be less. So we can say that the size of the cation is always less than the size of the parent atom. In our last slide, I have shown you that the cation is of smaller size than the parent atom. Likewise, we know if an anion is formed, as the number of electrons are getting added in the valence cell, so the size of the ion will be more, because here the resultant nuclear charge felt by the anion will be less because of the presence of the more electron. This also we will be able to tell using Slater's rule. So for fluorine, which forms the F-, you can see the sigma value when it is fluorine, it will be 0.0 into 0.35 into 6 from here, and then 2 into 0.85, so it is 3.80, and Z star will be 9 minus 3.80, so it will be 5.20. Now if instead of fluorine it is F-, then what will be the contribution? Here it will be number of electrons will be 8, and so we will be writing it as 0.35 into 7 from this group, and then again 0.85 into 2 for this inside 1s part, and then the resultant will be 4.15. So you can see that Z star is becoming 9 minus 4.15, giving rise to 4.85, which is much less than 5.20. So what is happening when we are going from fluorine to fluoride? The Z star is becoming less. So as the Z star is less, that means obviously the atomic size will be more for F minus. So using Slater's rule, we can say that the anion is larger in size than the another actually application of Slater rule. So it tells us that atomic and ionic size of elements of S and P block elements decrease along a period. This we will be able to tell using Slater's rule. We know this is the periodic variation, but quantitatively we can tell this using the calculation of sigma value and thus the Z star value. So for example, let us take lithium and beryllium. Both are present in period 2, and one is in group 1 and another one, the beryllium, is in group 2. So if we calculate the Z star value, you see for lithium it is 1.25, which is in group 1, and for beryllium it will be 1.95. That means for beryllium the Z star is more. If the Z star is more, we know very well that the size of the atom will be less. So Z star for beryllium is greater than Z star for lithium. So the size of beryllium will be less than that of lithium. So we can say that as we are going from left to right in a period, the atomic size decreases as the effective nuclear charge increases. Another application of Slater's rule is that we can tell that the ionization potential, electron affinity, trend in the periodic table we can explain using Slater's rule. All these physical properties are basically related with the atomic size, and this atomic size basically depends on the effective nuclear charge of the atom. So here I have chosen in period 3 some of the elements like phosphorus, sulfur, chlorine and argon. You can calculate the effective nuclear charge for these atoms and you will be able to get these values, and you see here for phosphorus it is 4.80, for sulfur it is 5.45, for chlorine this is 6.10, and for argon this is 6.75. So you can see very well that the Z star value is increasing as we are going left to right in a period. What is the meaning? Meaning is that the atomic size will be less, and if the Z star is more, you can understand the ionization potential, that is the amount of energy needed to knock out one electron from the valence shell, will be obviously more, and the electron affinity for these atoms will be also more. So likewise we will be able to explain all the trends of these physical properties in the periodic table using the Slater's rule. So let us come to another point. The successive ionization potentials have an increasing trend. So this we will be able to tell quantitatively using the Slater's rule again. So let us consider the case for aluminium. So aluminium, which is having atomic number 13, actually we can supply the ionization potential, that is the ionization energy value, to make a unipositive ion for aluminium. And when this unipositive ion is again supplied with IP2, that means the second ionization energy or ionization potential, it will give rise to aluminium plus 2 ion. So we have to actually tell that the successive ionization potential energy is more. That means IP2 will be more than IP1. So how we are going to tell? we have to calculate the Z star for both aluminium and aluminium plus 1. So here I have written the group electronic configuration for aluminium and aluminium plus 1. One electron is less here. You can look at here. Now we are going to calculate the sigma. So you can look critically here, and what we have found the Z star value for aluminium as 3.50. Now coming to the aluminium plus 1. Here the sigma value we have got 9.15 and the Z star value for aluminium plus 1 will be thus 3.85. So looking at this Z star value, we can say that the Z star for aluminium plus is more than the Z star for aluminium. What is the meaning? The meaning will be that more energy will be needed to pull out one electron from this aluminium plus ion. So that means this IP2 or ionization energy, which is the second ionization energy, will be more than the first ionization energy. So using Slater's rule, we could tell that the successive ionization potentials or ionization energies have an increasing trend. So this is the last application I am going to tell you using Slater's rule how we can tell that the ns atomic orbital is filled prior to the n-1 d atomic orbital. Here we have taken the example of potassium, which is having the atomic number 19. So for potassium we will be writing two kind of electronic configuration. In one we will be showing that we have entered the last electron in the 4s orbital, and this we are given the term as configuration A. And other than that, we can have another configuration where we can put the last electron in the 3d orbital, and we have termed this as configuration B. You can do it by your own. You just calculate the Z star value for this configuration and also calculate the Z star value for this calculation. So I have ended up to a Z star of 2.20 for configuration A and Z star is equal to 1 for configuration B. What is the meaning of that? So you know, as the Z star will be more, the stability of any electronic configuration will be obviously more. So here if we put the electron in 4s orbital, that means here Z star is more, so the stability of this electronic configuration will be more. So the atom will be stable when we will put the electron in the ns orbital instead of n-1 d orbital. So this is a very good example where we can apply Slater's rule and we can show that the electronic configuration which we write considering the energy rules is actually right. And so till now I have told you so many applications of Slater rule, and you should remember all the applications and you will be able to apply them in all the problems given in the exams. So here I have written some of the questions which generally comes in the examination. Other than these also there could be several questions using Slater's rule. And here you see I have written find the shielding constant of 3d and 4s electron in zinc atom. This could be any atom. And then calculate the Z star experienced by 5s electron and 4d electron in silver atom, where Z is given, Z is equal to 47. Slater rules, state Slater rules, and using this calculate the effective nuclear charge for one 3d and one 4s electron of iron. Again, another question is that using Slater's rule, justify that the electronic configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and not this 3d1. So students, I hope now you will be able to write everything about Slater's rule and you will be able to apply this for solving the problems related to the Slater's rule. and thank you and see you in the next class.